Hello everyone, welcome to another video from concept to circuit. You are looking at the network analyzer we are going to make using ADALM Pluto in this video. These plots are showing the measurements of S21 and S11 of the device under test, which is a 1.5 GHz RF filter. You can easily see the cutoff frequency of the filter. You can also see up to 1.5 GHz, which is the operating region of the filter. S11, measured S11 is below minus 10 dB. This is a very interesting device because it gives us the ability to measure S11 and S21 in gigahertz regions using ADALM Pluto and a chip RF bridge. So first, we are going to see what is S11 and S21, then how we can measure them, then how a network analyzer works and calibrates to reduce the error in the measurement, and finally we are going to look at the implementations in the code. So let's go. Okay. So let's talk a little bit about transmission line theory and what are the methods and ways we try to model them and use them when we are designing high frequency circuits. As you know, when the frequency is high, if you want to look at the voltages as waves, what happens is that the wavelength of the voltage becomes small, meaning that in a very short distance, the wave may cycle through its entire period. So it may change, the voltage may change in a very short distance. And this effect, it doesn't allow us to use KVL, KCL, or Kirchhoff equations that we usually use to calculate the voltages and currents in circuits. What we need to do is account for this limited, this short wavelength of the signals in when they are high frequency, and we need to account what happens to their phase, to their amplitude as they travel a distance. This is transmission line theory. Basically, what we want to do is that now a track or a wire is not just a wire that the voltage across it is equal. The voltage may be different if you look at different points at this wire. And this is one of the ways to model this is using transmission lines, because now the wires are transmission line, and as the voltages are traveling across them, their phase and their amplitude changes. Usually, if we want to simplify our transmission line and assume that okay, our transmission line is lossless, so as the voltage or wave is traveling, its amplitude is not changing, we can assume there are no resistances or conductances in the path. But still, to account for the phase change of the voltage, transmission lines can be modeled by a small segments, each segment consisting of inductors, an inductor and a capacitor. When the transmission is lossy due to skin effect, dielectric loss, or other effect, a resistor and a conductor are added to this. But for now, just let's say we just our transmission line is lossless, and we just use an inductor and a capacitor to model it. Now, as I mentioned, this is a very small segment. So if this is our axis Z, it's just from Z to Z plus delta Z, delta being a small number. You can see if I want to drive the voltage and current equations, because now voltage at Z plus delta Z is different from Z. And the way I can calculate it is this delta V is across this inductor So delta V across, so Z here is just like X, meaning that it's a distance, a derivative in distance. You can see it's just L di, but di over dt, which is di is the current passing through it. Also the same you can write for the capacitance, because the delta I from this point to this point is just the current passing through this capacitance, which is di over dx is minus c dv over dt. The signs are just definitely can change based on the definitions you have for delta v or your current. But the main thing here is the relationship between the voltage and the current in this in over x and over t. And if you want to using these two equations, what you can do is that you can instead of di here, you can replace di from this equation, which is you just need to put dx here, which is dx multiplied by this term, and then replace it to this in this equation. And you will end up in the wave equation. D2b over dx2 is equal to LCD2v over dt2. This is a wave equation, meaning that as this wave, so meaning that now my voltage is a wave, and its phase changes as it's traveling from z to point z plus delta z. You can find the equation, the wave equation from this equation, which it ends up to a general a solution of the wave, which is a e by power of j omega t minus kx plus by power of j omega t plus kx, right? This is the wave equation showing that now I have two waves. One is a wave going forward and another wave going backward. And the amount of A and B, the way that we calculate them is based on the boundary conditions we have at our two boundaries, which are Z and Z plus delta Z. So then if you assume at boundaries Z plus delta Z, there is a load ZL, you can, using this equation, you can calculate the reflection coefficient, which is gamma, which is what's the ratio of the forward wave, how much of the forward wave is getting reflected back. Gamma would be equal to ZL minus Z naught over ZL plus Z naught. Z naught, we call it a characteristic impedance of the transmission line, which from these equations, you can calculate it to be a square root of L over C. So for reflection, what we are interested in is the ratio, how much of the forward wave, the wave that is going to the load due to the mismatch at the load will be reflected back, which is our gamma, which the equation shows that it's ZL minus Z naught over ZL plus Z naught. So if you know gamma or S11, you know what's the load impedance. So now we want to make our ADALM Pluto to measure S11 and S21 for us. S21, we talked about it in the previous video, which is the gain from the input of the circuit to its output, which is just the frequency transfer function of the device over frequency, right? When both load and the input are uh, matched to 50 ohm, or Z naught, which is our characteristic impedance. So how we can measure them? In the previous video, we talked about how we can make a frequency analyzer which measures S21 using the lock-in amplifier we made. Basically, we send a tone which is it can be at different frequencies using our ADALM Pluto. Then that transmitted signal is connected to the input of the device that we are interested to find its transfer function. Then its output is connected to our ADALM Pluto receiver. Then based on that, we can measure how much is the received amplitude and measure S21. We can do the same when we want to measure S11, but here, what we need to do is we need another type of device that can give us the reflected wave from the device. So that when the transmitted wave, which is coming from our ADALM Pluto transmitter, connects to the device, we are interested in a device that can show us how much is the reflected wave. And then if we connect that reflected wave to one of our receiver channels, we can measure also S11. One last thing is that always, if we want to measure S11 or S21, there is always inaccuracies because of the cables we have in the line, or if we have some attenuators or we have some adapters and their mismatch or their loss may change my transfer function. So what I need to do is that once I have this device that has the ability to measure S21 and S11, I need a calibration method to calibrate whatever loss or other inaccuracies I have in my system and cancels them from the results. So when I'm looking at the measured amplitudes, I just look at the amplitude change that is only caused from the device that I'm interested in measuring, its S11 and S21. For calibrating S21, we are going to see we needed full calibration, meaning that we just, instead of a device, we just put an adapter that connects input to output with a gain of 1, so we can calibrate whatever loss we have in the cables and then cancel them from the measured S21. Also for S11 measurement, we need calibration when the whole wave is reflected back or none of it is reflected back. The condition, if I want to show here, condition that all the wave is reflected back can be thought of as, for instance, ZL to be open, meaning that there is no ZL. So this gamma becomes 1. So all of the wave is reflected back, which we call it open calibration. Or when none of the wave is reflected back, when ZL is equal to Z naught, our characteristic impedance, so gamma becomes 0. So then once in S11 calibration, we find the calibration ratio when we are measuring open and load, we correct the result, and that would be our network analysis. So now one other thing I want to talk about is how we can measure the reflected wave. Uh, there are different methods to measure the wave that is getting reflected. For instance, there is a device called a directional coupler. And what this device does is we have this transmission line that basically has a very a small loss. So whatever signal we have at its input appears at the output. But due to some mechanism, for instance, making another transmission line very close to this transmission line so they can couple through each other, we can make a device so a very small fraction of the input wave uh, reflects back, not reflect, it goes back to the other port, which we call it the coupled port, right? So that way we can measure the reflected wave. So what we do is that this device we connect it this way. So as the signal is traveling to the device that I'm interested in, whatever signal is getting reflected back is another source, which is just which you can assume is just I connect another voltage source at this port. And I know that if I connect a signal at this port, some of it is coupled through this port, and I can measure if I know the ratio of the coupled signal, I can measure how much is the reflected wave. There are many directional couplers you can buy or make, or there are many ways to implement them. But for this video, we are going to look at another method which gives us the ability to create a wideband reflector measurement using cheaper devices. Because usually these directional couplers, especially if you want them to have very good um, uh, low loss and wideband, they can become expensive. But one other way is to using a simple bridge to measure your unknown uh, resistance or impedance. So this bridge, what it does is that you just connect the voltage at its two port shown here, and if R1 and you measure the voltage at these 2 points here, which is our V out. So this, what happens is that in this bridge, when R1 over R2 becomes equal to R3 over Rx, the differential voltage seen here becomes 0. And that way, for instance, if you make all R1, R2, and R3 equal to, let's say, 50 ohm or your Z naught, you can measure based on the voltage you read, you can find how much is Rx. For instance, if Rx becomes equal to R1, R3, and R2, the voltage becomes 0. Right? This is one of the ways you can measure the input impedance or basically in a reflected amplitude of the device using this bridge. And usually you can, to up to some good amount of frequencies, you can use very small resistors, surface mount resistors that have low parasitics to create these 50 ohms and create a bridge that not only is cheap, but also it has a wideband ability. It can work up to several gigahertz. I'll show what's the bridge I'm using for this video, which I bought from Amazon. It's a very cheap RF bridge, and I show how it's made. But definitely there are some limitations to this bridge because one of the things is that there is a differential to single-ended conversion you need to do, because here you are measuring these two voltages with respect to each other. And if you want to make the voltage with respect to ground, you need to make a differential to single-ended conversion requiring, for instance, here it's shown as an active amplifier, but if you want to use higher frequencies, sometimes they use a balloon to create that differential to single-ended, and that balloon by itself has a transfer function. It's not an ideal differential to single-ended that can operate at all the frequencies. Or these resistors, definitely they have their parasitics of themselves. Therefore, this bridge comes short in some of the, if you make it, it may not operate as well as the directional coupler at some frequencies due to limitations of the balloon or the resistors. But just for the beginning of our journey to make a very cheap and good network analyzer, we start with this one, and then we create our way to a much better approach. So then I just want to go over like some of the key implementations. This lock-in detection I've extensively talked about in the previous videos. Please, if you haven't watched the previous videos, please go and watch the videos that I talk about creating a spectrum analyzer or a frequency analyzer. I also put their link in the comment down below. But basically, we want to create a sine tone at the output of the ADALM Pluto. So basically, in baseband, we create a very uh, uh, low frequency sine tone, for instance, 500 kilohertz. Then we change the TXLO to the frequency of our interest. Then at the receiver, we first make the RXLO equal to the TXLO that we are interested in looking at. Then we multiply the inverse of the baseband sine tone we created to the received data, and then we make a very narrow low pass filter to eliminate all the noises, especially thermal noises, and measure the amplitude. So now that we can measure the amplitude at our receiver port, what we are going to do is connect our TX to the input of the device. Then the output of the device is connected to my first RX port, and the output of the RF bridge is connected to another RX port of my ADALM Pluto. Then what I do is just I measure the received amplitude as the TX frequency is changing and the sine tone frequency, which is the input to the device, is changing. So based on this, if I didn't have any loss or mismatch in my system, I could just use this measured amplitudes to measure S11 and S21 and S11. But what I need to do is that I need to find the loss in my system, and I cancel them out from these values. So I found the true effect of the device, not something else. So for calibration, I just, instead of the device, I just connect the TX to my first receiver port using a through connection, which is just a very a small loss adapter, and just I measure what's the amplitude I'm measuring. Then I save this, and I know that okay, if I don't have anything in my system, this is the amplitude I'm measuring. So now that I have S21 measurement, calibration measurements, whenever I want to, after the calibration, whenever I want to measure the actual S21, what I do is whatever amplitude I find, I just deduct that amplitude from the calibrated amplitude to come up with the effect, with the device effect only. So this is my calibration for S21. And also for S11, as I mentioned, we need 2 points. One, when I have all the reflections, all of the signal is being reflected back. So I'm measuring the maximum uh, amplitude. And then when it's the load is equal to my transmission line characteristic impedance, so none of the voltage is reflected back. Once I have those numbers, I can also calibrate my S11 measurements. One other thing I added to this software is because of some of the non-idealities of the RF bridge, it's not always that for open, which is when there is no load um, at the receiver, I get all the time higher amplitudes compared to when it's low, because the directivity of the RF bridge, due to some non-ideal effects or the parasitics, is not always guaranteeing this equation for me. So what I do is that whenever my open and load in the calibration I'm doing get their amplitudes get very close to each other, I just mark those points as the points that I know based on my calibration are the points that I cannot rely on in my measurements from this RF bridge. So I just skip those points when I'm sweeping. So one, as I mentioned, for calibration of S21, I just deduct those from the raw measurement, those calibrated values from the raw measurements. I also added some interpolation. So in case that the frequency of measurement is not in my calibration frequencies, I just interpolate them, the frequency from the points I have. Also for S11 measurement, once you know what's the amplitude you have for open and load, you can measure gamma, can calibrate gamma based on load and open by just this equation A minus L over O minus L. So for instance, let's say A here is when I connected open to my load. So open here, the numerator becomes O minus L, and then denominator is also O minus L, so gamma becomes 1, which is correct. Also, assuming that I have connected my device to load, which is 50 ohm, so A becomes L, so L minus L becomes 0, then gamma becomes 0. So these 2 points can give me this equation to calibrate gamma for the device. And as mentioned, we are skipping the points that these two become close, because as you can see also, O minus L comes in the denominator for me, and if this is close to 0, it may make gamma very large and inaccurate. But as I mentioned, for the first try, we used a very cheap RF bridge here, and it's giving us some good results for some frequencies. But definitely, we want to improve this further so that if we, for instance, use a directional coupler, we may not end up to this scenario that O minus L, at least to that operation, that the guaranteed operating frequencies, O minus L won't become too small. Okay, so I just wanted to talk about this, and now let's go and look at the RF bridge. I just want to very briefly talk about the RF bridge and then run the code one more time. As I mentioned, can create a resistive bridge to make reflection measurements and create our S11 measurement based on that. And because we can get access to relatively cheap components, surface mount components, resistors with low parasitics, this resistive bridge can operate at relatively wide band operations. But one of the issue here is that the output of this bridge is a differential voltage that needs to be converted to single-ended. And and this is a challenging part because especially as we go to higher frequencies, having an amplifier that can operate, let's say our ADALM Pluto from 100 megahertz to 3 gigahertz and amplify this signal and create uh, a single-ended version. This amplifier is not a cheap or relatively easy to make amplifier. One idea is we can use another type of device that in RF design is usually used. It's called balun. Balun is essentially by using RF transformers, we can create a differential to single-ended conversion. And these baluns are used uh, in many applications in RF design, either in discrete implementations or integrated versions. So this balun, which is essentially a type of RF transformer, can get connected to our differential voltage here and output the single-ended version. The other side can be defined as ground. Then what we have is we have this 250 ohm resistor. Then we want to also have 50 ohms on both sides of the this branch. And to one side, we connect the device under test. And to the other side, which is our reference, we just can terminate it via a 50 ohm resistor. And therefore, based on our device under test impedance, the voltage, this differential voltage changes, and after the balun, it becomes single-ended. Then when we connect this to our ADALM Pluto, we can convert this, we can read and calculate this voltage amplitude and measure our S11. And initially, in this project, I bought this very cheap RF bridge from Amazon. which claims to operate from this is 0.1 to 3000 megahertz. And this is the balloon, this part here that is connected to this here is called out, which gets connected to our ADALM Pluto. This is the input, and the reference side we just terminated with a 50 ohm resistor, and DUT is the device, our device that we want to measure is S1. For initially, I use this bridge, but um, as we go on, I show that this bridge I didn't get very good behavior from it across all the operating region, which uh, causes some inaccuracies in our measurement. But to get a more comprehensive explanations, because I don't want to make this video very long, I thought to make the video of creating network analyzer into separate parts, where initially in this video I talk about the basics and the fundamentals of what and how we can make the network analyzer. And then in the next video, I'll go into more details about this RF bridge, and we actually measure its frequency response. And also we go in more details of the actual code. I already showed the parts of the code that were critical. And as always, I'm also uploading the entire code into our from concept to circuit GitHub. But I just leave the more detailed examination of this RF bridge and the code, and also the full operation of our network analyzer to the next video. So talking about all of this, now let's go to our network analyzer. I just want to describe what each part does one more time before ending the video, so that we get a better understanding of the structure. Okay, now you are seeing the software running and also the setup. I just want to talk about the setup a little bit. So we have our ADALM Pluto, and the TX channel is going down to the RF bridge, and the RF bridge, the output of the balloon is connected to the second ADALM Pluto RX. I have added an attenuator in the path, and because the calibration will take care of whatever attenuation we have in the path, I don't worry about that, but I just put the attenuator so that in case that there is high voltages here, it doesn't damage the ADALM Pluto. And you can see the 50 ohm termination here, which is connected to the reference side. Then the device under test is connected to this filter, a 1.5 gigahertz filter, which is the device we are measuring right now. So whatever reflection is happening due to the input impedance of this filter is changing the voltage at the output here. And also to measure S21, which is the gain of the filter, because the transmitted wave, some of it also enters my DUT. I just I have connected the first RX channel of the ADALM Pluto to the output of the filter. This way I can measure S11 and S21 of this device at the same time using ADALM Pluto. And also here is another attenuator, 30 dB attenuator before it connects to the RX. So this is a setup, and you see the results of S11 and S21. In the next video, I will go over the calibration phase once. It's just simply for S21. What we do is we replace this filter which is our device under test, with a true connector, which is just an adapter connecting DUT to our attenuator. So whatever attenuation we have in the path, it's getting calibrated. The same thing for S11. Basically, instead of for S11 calibration, we have two ways. One is when we just remove this filter, we connect the 50 ohm termination at the device under test, and another phase is just we leave this DUT open. What happens is that we know that when DUT is open, uh, the S11 that we should read is 0 dB because all of the wave is reflecting back. And we know that in the termination, when it's perfectly terminated, we need to see 0 reflected wave. So based on that and the equations we described in the beginning of the video, we can easily calibrate whatever attenuation we have in the path so that the S11 we measure would be uh, uh, ideal. So there you have it. This is the first video we talk about the network analyzer that we made. I'm putting this on GitHub, so it's an open source project. Please feel free to subscribe and contribute to the channel by um, leaving me a comment, sharing this video because it helps a lot. And also, this is a very interesting project because um, up to 3 gigahertz, we are making a network analyzer with only an RF with an RF bridge, which is $30 bridge, and our ADALM Pluto with a somewhat reasonable accuracy. I'll go over what's the resolution and accuracy we can get from this in the next videos. Yes, so tune in for the next video where we also go into more detail of the code and actually how is the calibration phase is done. And I plan to, after we characterize this RF bridge, we go over we go over using other RF bridges or even directional couplers. But you can see even with this RF bridge, if you look at the plots, we are getting very good S11s up to below minus 10 dB up to 1.5 gigahertz, which is the operating region of the filter. And also for S21, we are around 1.5. We are measuring the drop happening here. Thank you.